Hello, welcome to class on April 9th. We're continuing going through the topics on the syllabus, and today our topic is measurement. And we're going to look at what is the nature of measurement, then we're going to look at the levels of measurement, and then we're going to look at how do we assess accuracy in measurement. Those will be our topics for the day. Now, first of all, measurement and where does it come into the course? Well, remember in the course, I've several times alluded to this diagram that this tells us what we do when we do research. And we start out with a hypothesis we want to test. Then we come up with a plan. How are we going to gather information to test that hypothesis? That's called research design. We spent about 5 or 6 classes on research design. Then what we have to do is our research design will lay out what observations we're going to make of the world, and that's what we do when we do measurement. We make observations of the world, and what we produce out of measurement is data. Data being the plural, datum is singular. So we make these observations and we produce these variables of data that we see in the world. Then we have to move up to data analysis. We take these data and we analyze them statistically, coming back to our original hypothesis. Did we confirm or disconfirm our original hypothesis? So that's where we are today with measurement. Let's dig into measurement now. What is measurement? Well, there are a couple definitions of measurement. Let me give you some of these definitions, starting with a definition by Professor Nachmias. Nachmias defines measurement as a procedure in which one assigns numerals, numbers, or other symbols to empirical properties according to rules. So what this is saying is we're going to assign, meaning we have these rules in the definition that when I observe such and such a thing, I'm going to assign this symbol to that thing that I just observed. And we use numerals or numbers in our measurement to assign some numeral or number to an observation. The difference is small. A numeral is when we use the number system and it doesn't contain a quantity of how much of something in it. So we have numerals on the backs of football players. We might not even have a football season this year. If a player has a 64 on their back and another player has a 32, it's not that the player that has a 64 has twice as much as something as the person that's 32. The numbers are just being used as numerals, as symbols, as opposed to when we use the number system as true numbers, say on body weight. If I weigh 400 and somebody else weighs 200, then that makes a difference. So if I weigh 400 pounds, that's just not a symbol. That measures the amount of something that I have when I'm measuring. There goes my alarm telling me I'm supposed to make this tape, and I'm doing it. I'm early. So this is the definition of Nachmias. Another definition of measurement is by Babby. Measurement is careful, deliberate observations of the real world for the purpose of describing objects and events in terms of attributes composing a variable. So it's careful, deliberate observation of the real world, what as opposed to the unreal world, but observations of the real world for the purpose of describing objects and events, things we see out in that real world, and we describe them in terms of attributes composing a variable. A variable is something that varies from case to case, and so we're going to observe and see differences on these attributes. That's how Babby looks at this definition of measurement. Now, in the definition of Nachmias, this idea of assigning according to rules, let's play with that a little bit. Assigning has this idea that we look out in the world and we see things happening and we have rules, we assign symbols to what we see out there. So that measurement is a kind of mapping. And when you have a map of the Washington, D.C. area, it shows the various structures and their relationship to each other. That's what we do when we measure, say, in social science. We do these measurements, we come up with a data matrix. Like you did in your first computer assignment. Remember those numbers that you typed into the data matrix? Well, The numbers in the data matrix are a kind of map of the reality where you've measured things. And that map is accurate if you've done your measurement properly. And what we do is we look within the data matrix and we look for patterns, and we tease out patterns because those are the actual patterns that exist out in the world. So that measurement is a kind of mapping. And what is involved in good measurement is that our data map accurately reflects what's out there in the real world. That's called isomorphism. Isomorphism is when the actual measurement data that we have accurately reflects what's out in the world. And that's what we want. Because when we don't have isomorphism, we don't have an accurate assessment of what's out in the world. And then we make inferences about the structures out in the world, and they're wrong because the data is wrong. That's why measurement is so basic to good research. Finally, this idea of mapping, it ties into something Galileo said. You don't know much about Galileo, Florence, Italy, 17th century. He is really the father of modern science. And it was Galileo that said, the book of nature is written in mathematical characters. That is, you can take mathematics, and if you accurately measure things through what he called experimental, and you get these numbers here, that it accurately reflects what's out there in the natural world. So we can use mathematics to look at the patterns of the data that we produced and understand what the structure of the world is. That's why science has become so wedded, I think, to mathematics, that we observe the world, we produce these data, then we can use mathematics to tease out the pattern. And that teasing of the pattern, if we've done this properly, reflects what the structure of the world is out there. And it's very important. Now, look at the nature of measurement. Now let's look at the kind of measurement we can do. And methodologists have come up and analyzed the kind of measurement we can do using this concept of the level of measurement. And this is the idea that we measure various variables and then we can categorize them and put them into levels of measurement. Levels has the idea that there's more information contained in one level as opposed to another level. And I can give you the categorization of the levels of measurement. I have it in another chart for here, and you can read it and look at it. I'm going to explain what it is. Over here, we put the kind of concepts. Remember, about a month ago in class, we talked about different kinds of concepts that we have here. Here's the classification concept. Then we have comparison concepts. Go across like this. And over here, we have quantification concepts. Now, in this next column, for each of the kind of concepts, we've designated what the level of measurement is, the terms we use to talk about that level of measurement at that conceptual level. We can see at this classification concept level, the level of measurement is called the nominal level of measurement. Some people use the word categorical level. They can be used interchangeably. And then I'm giving you some examples. What do I have here? Gender and religion as examples. So think of what comparison concepts are like. We make observations of things in the world. We apply this concept, say, called religion. And then when we apply it, we put people into categories, religious categories. And think of how much information there's contained at this level of measurement. It's not very much. We can take two people and we have their measurement of religion, place them side by side, and what can we say? We can say either they're the same or they're not the same on religion. That's all we can say. That's not much. And we'll see when we get down to the levels of measurement that have more information, that we can make more statements about people when we have measurement at a higher level of measurement. Now, let's go down to the comparison concepts. We're getting more complex here. The level of measurement, when you measure a comparison concept, is called the ordinal level of measurement. And what's involved with that is you've measured things on a scale of something from a greater or a lesser amount of something. A common ordinal level of measurement that you're used to is the grading system we've used in your educational system, A, B, C, D, E, F. That is, it exists along a scale in which there's more or less of something as you move along the scale. some other examples I put down here. LibCon that we measured in class. Remember in our first computer assignment, we measured liberal and conservative along a scale from 1 to 7, a common way that it's measured. Say, University of Michigan's American National Election Study. We used it in our first computer assignment. Then the thermometer scales. We didn't get to the thermometer scales yet, but the American National Election Study has a scale. And they tell people it goes from 100, where you're very cold towards something, to 100. It goes from 0, where you're very cold to something, to 100, where you're very hot on something. And then you throw out something like Vice President Biden. Where do you put them on the scale? Oh, I put him in a 70. President Trump. Oh, hate the guy. I put him in a 0. This is how the thermometer scale works. And you generate data at the ordinal level of measurement along a scale of some kind. Now, let's go to the more complex, the highest level of measurement. That would be a quantification concept. And when we measure things at the quantification concept, we get the interval level and the ratio level. They're not quite interchangeable. For our purposes, there's not really that important a difference. The real difference is this. The ratio, you've got a quantification level of measurement. You're measuring something, and you usually have a unit of measure, like pounds or temperature, degrees, things like that. In the ratio level of measurement, you have a true 0 point, where you get smaller and smaller amount of something and you get to 0 and you can't get any less. The interval level of measurement, it's quantifiable, just like the ratio level, but in the interval level, you don't have a true 0 point. Let's take some examples of at this quantification level. Weight, votes, GDP. These are true quantification kind of concepts. Now, the difference in interval ratio level is the ratio has a true 0 point. Think of some measurements in which you have a true 0 point, and some in which you don't have a true 0 point. Take temperature measured in degrees Fahrenheit. I just looked at the weather here. It's 50 degrees here in Columbia, Maryland. Well, it could be 50, and then it could be lower than that. It could go down to 40, 30, 20, 10, 0. Then it can keep going. It can keep going lower than 0, -10, -20. So that is what we call an interval level of measurement, where you have that kind of measurement. Now, a ratio level of measurement has a true 0 point. Say my body weight. My wife and I weigh in each Sunday. I weighed in 198.6 last Sunday. You could lose weight and go 190, 180, 100, 50, 40, 0. You can't go into the negatives on body weight. So body weight is this true ratio level of measurement, and it makes a difference. You can make statements about the ratio this case is to that case. So for instance, take a ratio measurement might be how strong are you in the bench press? Well, we can have person John, who bench presses 400, and Doug, who bench presses 200. We can say that John can bench press twice as much as Doug. We can make those ratio kinds of statements. You can't really make those statements at the interval level of measurement. No. If it's 50 degrees Fahrenheit outside, and then in somebody else's city it's 25 degrees Fahrenheit, you can't really say it's twice as hot here in Maryland as it was in this other city. Now, scientists like the ratio level of measurement, so to get around that problem we have with degrees Fahrenheit, have the same problem with degrees centigrade, they've come up with their own scale, a true ratio scale to measure temperature. Anybody familiar with degrees Kelvin? Degrees Kelvin is you measure things and you measure how much scientists think that temperature really is the speed with which the atoms are moving. And what you do is get colder and colder and colder, and you get to the point where you can't get any colder. The atoms don't have any motion to them at all. That's defined 0 degrees Kelvin. So scientists have come up with this ratio kind of measurement like this. Now, another thing to notice about this is that as you move down here, these variables that are measured at these higher levels of measurement, there's much more information contained in them, and you can make much more important statements about two objects when you have measurement at this quantification level than when you have it at the classification level. So at the classification level of measurement, take something like religion, and you have two people's religion. Well, you put them side by side. What statements can you make when you compare them? Well, you can say they're either the same or not the same on religion. It's all about all you can say because there's not much information contained at this nominal level measurement. Now, take a comparison concept like grading. Somebody got an A on the final and somebody got a C. Well, you can make all the statements you made up here at the nominal level measurement. They didn't get the same grade. You can say that. But you can say more now. You can say this person that got an A did better than that person that got a C because you have measurement along a scale like that. There's more information contained in it. Then finally, when you go down to the quantification level like that, and say we have weight on the bench press, the example I used before. John does 400 pounds, Doug does 200 pounds. Well, you can make all the statements you made at the nominal level. They're not the same on their strength and bench press. You can say that. You can make ordinal kinds of statements saying, John's stronger than Doug on the bench press. You can make that. But you can now make more. You can say that John is twice as strong on the bench press as Doug is. And that becomes important later when we move over to talk about data analysis, because the mathematicians have told us that when we get to the higher levels of measurement, there's much more sophisticated mathematical techniques we can use to analyze this research data. And we'll see that when we get into the data analysis part of the course. Another point I want to make about ordinal level of measurement. We move along a scale and we place things on a scale. There's a number of common ordinal levels of measurement techniques that you're probably familiar with, or you should be familiar with. This one here is called the Likert scale, commonly used in social science. And we have this scale where we want to measure someone's attitude, and then we give them from 1 to 5. Where if they put a 1, they agree strongly with the statement you're going to tell them about. 2 is agree somewhat, 3 is neutral, 4 is disagree somewhat, 5 is disagreed strongly. Maybe you've seen that technique. It's used in the American National Election Study. So for instance, in the American National Election Study, random sample of over 2,000 people are asked all kinds of questions about politics. Here's a Likert scale question they ask people. They give him this scale and they ask him, do you disagree or agree with this statement? And they read the statement, men are just better cut out than women for important positions in society. And then people put their answer on this scale like that. And there are all kinds of attitudes that are measured that way. In your course evaluations, as they were commonly done here at GWU, they use Likert scaling to get people's, whether they disagree or agree with statements about the course. That's one way of scaling in an ordinal level of measurement. There's another ordinal level of measurement called the semantic differential. Maybe you're familiar with that. We try to get people's attitude towards objects on a scale like this, where we have the semantic differential means we have opposite descriptive adjectives at the end there. And we try to see where do people place themselves on this scale like this. I worked on a research project in which they did a poll of people that were OBGYN docs, and they wanted to know, how did they like being an OBGYN doc? That's useful for people who are in medical school or thinking of specializing, to know what the people that are in that specialty think. And we would ask people like questions like, well, how do you feel in your job as a OBGYN doc? And important or unimportant, people check where they feel along there. Do you feel disorganized in your job or organized? You put a check in there. Useful or useless? Put a check in here. That's the semantic differential. It's a common ordinal method for measuring people's attitudes on things. Now, another issue I want to talk about in terms of measurement is single indicator versus multiple indicator measurement. Meaning we have a concept, and sometimes we can measure that concept with just one indicator out there. Sometimes it doesn't do justice to the concept. We have to use multiple indicator. So for instance, take on the American National Election Study. They want to know the gender of the respondent. And the person just checks a box, male or female, or maybe they're expanding it to include those 64 genders that your generation has now invented. I don't know. I haven't seen the American National Election Study going on for this year. But that's a single indicator measurement. And in that research setting, that's adequate for us to measure something like sex or gender. Uh, Other people have to be more vigorous when they measure this. Like, for instance, in athletic competitions, we separate men and women. How do we measure that difference? Do we let them just check a box? Uh, this issue has come up with transgendered people, males who are transgendering to be females and run with the females. A number of them have cleaned up in female athletics. There's a brouhaha about that. The Olympic Games has this issue. How do we decide whether someone can run with the women in the Olympics or the men? I'm disappointed the Olympics have been called off. I've been watching the Olympics since 1956 when I was a kid, when they took place in Italy. Always fascinated with them. How do they differentiate whether women and men can run? Well, it used to be they didn't go into detail, scientific detail. Now it's much more detailed. For a long time, if you had a Y chromosome, you had to run with the men. Now they do fancy biochemical exams on people's blood, looking at things like testosterone. So they need more of a multiple indicator measurement. And this issue becomes an important issue in many situations. Uh, Use a typical multiple indicator measurement in which you could only get accurate measurement through multiple indicators. I would use the example of testing. Testing in school. You've been taking tests for years. A test is a measurement technique. So sometimes when you're thinking about models of measurement in these issues, think of testing. Think of your final exam. Now, it'll be unusual this time because it'll be a take-home final, but usually we do an in-class final at the time that the deans designate. The dean's defining a final exam as a significant academic experience. So, okay, I give you that significant academic experience. What happens if, well, usually I give it in the form when you're in class, like the midterm, when you have those various parts, true or false, some definitions of terms, great. Only it has to be beefier for a final exam because it has to be that significant academic experience. So, what if you'd come into the final exam and you look and there's a piece of paper? Answer the question, what is isomorphism? Well, I just had defined it for you, right? And that's all there is on the exam. You answer that and leave. People get it right, get 100. Some people get 0. They get it wrong. What if you got a 0 on that final exam? It'd really bring your grade down. You might not even pass this course, even with a pass-fail trick that GW's administration is giving you. So what would you do if you missed that question and you got an F in this course? I think you'd be angry about it. And think of why you'd be justifiably angry. It's because on that final exam, it's a measuring technique, and it's a typical multiple indicator measuring technique. There should be many questions. We should touch on some research design. We should touch upon science. And what is science? We should touch on measurement. And then we're still going to do data analysis. You have to touch on all those parts with multiple indicators to get a true measurement of what things are like and how you've done in the course. That's a typical multiple indicator measurement. Now, final topic for measurement is accuracy in measurement. We want to measure accurately. If we haven't measured accurately, we haven't measured properly, and we can make inferences about the world because we've mapped the world incorrectly. What methodologists have come up are 2 concepts to decide accuracy in measurement. One is reliability and one is validity. Let me talk about both of those. Reliability is the extent to which a measuring instrument is consistent when measuring 2 identical objects or measuring the same object at 2 times in which it has not changed. Are you consistent? Do you get the same measurement under those circumstances? So think, you got two identical objects. If your measuring instrument has reliability, you should get the same measurement when you measure them. Or if we have one object, we measure it at point A, and then we measured at point B and it hasn't changed, you should get the same measurement. That's reliability. It has to do with consistency in measurement, and there are reliability problems in measurement. Be aware of them. I had just brought up the Olympic Games, right? I like the Olympic Games. I like all the things, but I'm really interested. I like platform diving. Ever look at that? Ever stand at that platform and look over the side? Oh my God, it's intimidating. And the way they do those flips and do those dives is pretty incredible. Well, in order for there to be a competition, we have to measure people's excellence in their dive to decide who gets the gold, the silver, and the bronze, right? How do they measure Olympic diving? You ever watch it? A person jumps off that platform, they do flips, they fall in the water, and they have you can't have me judge it. What do I know, right? You have to have an expert. And what they have is they've come up with a scale from 0 to 10, where 10 is just the best perfect dive, and 0 is you just flubbed it. You did a belly flop, Doug would do, right? So you could have a person look up there and people do a dive and they give them a 9.3, right? But there's another judge equally qualified says, I think that's an 8.2. And another judge that might think, no, I think it's a 7.4. How do we deal with this problem? This is a reliability problem. Well, what we've done is we take 7 judges. They watch the same dive and each of them put up a score. And then what happens is those scores are different. Those scores are different because we have a reliability problem in our measuring technique here. How does the Olympic Games, how do they deal with it? They take the seven scores, they throw out the lower 2, they throw out the upper 2, and those middle 3, they take an average of the middle 3. That's how they've come up with how to deal with reliability. We have that in daily life, that we got to deal with reliability. Remember I told you my wife and I weigh ourselves every Sunday morning before breakfast, and we'd write it down on the wall. We need an accurate scale. For a long time, I had a scale that was kind of old-fashioned. It had a spring in it. You step on it, it spins around the numbers, and there's a line. Boom, you read it out. There was my scale. Then I had a friend who was really big, a big man, and he got on that scale, and it mashed that spring down and broke my scale. And, well, I could say, what the hell? I have to join the 21st century. I need a digital scale. So I spent 55 or 60 bucks at Sears, and I bought a digital scale with an LED readout. And I get that thing home. On Sunday, I get on it, 198. I get off, I get on, 196. I get off for 9, 199. I haven't changed in between going on and off, except way over in the 9th decimal point. My weight hasn't changed. The scale's got a reliability problem. How do you deal with it? Well, my wife says what you should do is get on and off until you get the number you like. Then write that one down. That's not methodologically sound to do that. What you do is you get on and off of it 3 times and you take that average. That's what I would do with something like that. Or you get a better scale. I spent $200 for a better scale when my sons were in high school on wrestling teams. They couldn't know within a pound or 2 pounds how much they weighed. They had to know within a tenth of a pound. So they had to know whether or not they should shave off their eyebrows if they're going to make weight for a wrestling match. So a more accurate, a more reliable measuring instrument is just going to cost more. Now, let's look at that other question, validity. What is validity? Validity is the degree to which the measuring instrument measures what it is supposed to measure. So take my scale. I get on and off of it, 150, 150, 150. It's got reliability. It's consistent. It doesn't have validity. I don't weigh 150 pounds. I haven't weighed that since I was a junior in high school. That's a validity problem. Now, to test reliability of a measuring instrument, we do test-retest method. We measure something, then we wait, then we measure it again, and we see if we get the same things. That's the sort of thing we do to test reliability. To test validity, it's more difficult. In testing validity, we split out validity into different kinds of validity according to how we try to assess them. So, for instance, take face validity. Face validity is when you look at a measuring instrument and you think, on the face of it, is it measuring what I intend to measure? That's face validity. Not a very strong kind of validity. Another validity would be sampling validity. That is, back to my final exam. The final exam would have sampling validity if we're taking indicators from each of the subtopics of my course and putting them on the exam. That would be sampling validity. And then finally, I want to talk about predictive validity. Predictive validity is when you have a measuring instrument, you measure something, and then you can say, there's certain predictions that should come true according to this measurement. Do they come true? That would be, take the SAT exam. What is it supposed to measure? It's supposed to measure when you're in high school, how are you going to do your first year? What's your GPA going to be? How are you going to do? So what we can do is to assess the predictive validity of the SAT is we have the SAT scores for a lot of people, thousands of them. Then we get their first year GPA and we look, are they connected or not? They should be correlated. The correlation is 0.50 between the SAT exam and a person's first year GPA. Probably stronger than most measurements, but the SAT has been under attack probably for different reasons than that. Now, this is what I have to tell you about measurement. And what I would do is go to the Blackboard, the discussion board, enter your comments and any questions, and I'll answer them. And next class, we're going to start to move on to data analysis. Enjoy yourselves.